Welcome to another fibre laser learning lab. No, I'm not in the wrong place. And you're right, this is not a fibre laser machine. But today we're going to do a little bit of an investigation because I had a problem just recently. As I mentioned in my other series, my stepdaughter is busy building a small business with this particular machine. And she's been engraving some slate, and I thought, hang on, the fibre laser does slate very, very quickly. This machine does it moderately quickly now that I've pimped it up, but surely we must be able to do a much, much quicker job on the fibre laser machine. I'm lost for words really, because the fibre laser machine has got a spot size of about 0.06 or better. This has got a spot size of about 0.1. So technically I should be able to run this slate on that machine over there much faster and with better quality. I've been doing a little bit of fiddling behind the scenes just very quickly, and I can't succeed. Now, question is, why can't I succeed? And that's what we're going to have a look at today. First of all, we're going to have a quick run on here and see what the quality is and what the dot is that I can produce on this machine for dithered engraving. And then we're going to take a look at why I can't achieve the same results on the fibre laser. Because I know that I can engrave slate on the fibre laser. It does a fantastic job of engraving text. But text is not the same as precision dots. And that's what I'm trying to establish, just what it is. I mean, I've tried all sorts of parameters on the fibre laser machine, so the only way to check it is to find out what dot I'm able to produce. So first of all, let's just have a look at the results that I get from this machine.
Just 254 dots per inch, or 254 pixels per inch on the image.
I think you'll agree that's a pretty good image. Now, I don't need to run that image on both machines. What I really need to do is to check the quality of the dots that I'm producing on this machine with this lens at this focus. So we'll just change the program and we'll just run my little dot test. Okay. It's as simple as that. So just so you can see where it is, look, there is the little dash and dot pattern. Here's what it looks like at 50 times magnification. There's a scale on this side here which is in 0.1 of a millimetre. And if I move that down onto there, we can probably just about see 0.1 of a millimetre. So these dots are about 0.1 of a millimetre diameter. Now they're 0.2 millimetre pitch. So it begins to make sense that we've got dots there that are about 0.1, and 0.1 allows me to generate a picture at 254 ppi, or 254 dots per inch. Now if we move off the dots, we've got single dots there, same sort of size, and then we've got these dashes. Now they're various size dashes. We should find that the dashes are 0.1 wide. And it's much easier to see them. We can see that they're roughly 0.1. But what you can't see there at that magnification is actually what's going on. There we go. I think we might have found something there. Now, first of all, you can see right along the centre there is a sort of a groove. Okay, it's not uniform all the way along, but that is the very high intensity part of the Gaussian focused beam. And on the side here, what we've got is something that probably, I would imagine, is like an eruption from a volcano. We've purged out the middle and we've blown it up onto the sides. But But what we need to do is just go in and look at that at a higher magnification, and then you'll see what's actually happening. Now, first of all, we've got our deep groove, and if we look in the bottom of the groove, there's a hint of what's going on down there. But when we come up to the top of the groove, just there, can you see all these bubbles that are existing along the side here? Now, those bubbles do not exist in the background, and they're obviously also a different colour. So what's going on? Well, this is slate, and slate started off its life as sediment in the bottom of an ocean. Sediment, sand, silicate of some sort, anyway. It gets compressed into a very dense material. It gets subducted below the Earth's crust, compressed to some fantastic pressures, and then over millions of years it works its way back up to the surface as some sort of mountain or hill and gets thrust up above the sea level. And that's how they managed to dig slate out of the sides of mountains. But the essence of it is, it starts off life as a sort of a sandy silicate material. And what do they make from sand and silicates? Glass. What we've actually done here, we've fused the material together and we've produced a glassy structure. And that's what those bubbles are. Those are bubbles in a gooey, glassy material that we've created when we heated the surface up. So that's not a white powder. That's actually a completely permanent grey glassy structure. Now there's a classic example of a single dot, and there you can see the bubbles of the glassy structure within that dot. Here we are on the fibre laser machine, and we know that 1 micron wavelength light is basically not going to pass through this material. It's opaque. And opaque basically means, let me give you that simple analogy that I mentioned to you before, that when a stone falls from the sky, it's completely harmless. The only time it's dangerous is when it hits you on the head. And at that point, when it collides with something solid, you get an energy transfer. Okay, the same applies to a light wave. When the light wave comes down here, only when it hits this solid surface will something happen. And 1 micron waves are adequate to vibrate the molecules in the surface of this material and cause them to heat up. So we know that the light is going to work on here. Can we get the energy concentrated in such a way that we can do my little dot test, for example? Technically, we should be able to do it because the focus on here is better than the focus on the continuous wave laser machine. Now, that's really the clue that gets me started on what the parameters should be for this machine. Now, this is a 20 watt fibre laser, and as I mentioned before, we used about 20 watts when we were doing the test here, and this little pattern just here. So here's the little dot program, and what we're going to try and do is to simulate the same conditions that we had over on the glass tube CO2 laser. So we're trying to achieve that with a speed of 400, power 100%. The frequency here doesn't really matter because we've got it set to 1000, but it's going to be ignored because what I've done, I've set the pulse width to 1 nanosecond. Now 1 nanosecond is a special code for this machine which basically switches it on continuously as CW mode, which is equivalent to the glass tube laser. So we've got an equivalent set of conditions here for the 10.6 CO2 laser, and now we're going to see if we can simulate the same sort of results on this fibre laser. We've got a little pattern. What we need to do is go and look at that under the microscope to see what we've got. Well, here we are at 50 times magnification, and we've got a scale here which at 50 times magnification shows that we have got a line which is roughly 0.1 millimeters wide. So it's doing roughly the same sort of job as the CO2 laser. It's not getting any better. I hoped it might be a little bit better, but in fact let's just have a look at the dots. As you can see, the dots are there, but they're pretty indistinct. They're merging into each other because the power down the centre here has exploded so much that the glass that's been created around the edge of the volcano has spilled over and joined the next dot. It gives the impression that I've actually got too much power there at 20 watts, and maybe I'll be able to control these dots much better if I start reducing the power. So this is a very good start. Previously, any work that I'd done on this machine just by eye had been based on using one of the pulse widths that were available on this machine. I hadn't used this continuous wave mode. Well, at 80% you can see we're still getting the glassy effect. We're getting slightly better separation of the dots. They're not spilling over quite as much as they did before, and that's 80%. So let's take a look what 70% looks like. It's getting a little bit better. We're seeing a little bit of better separation. That's 70%. Let's try 60%. Still rather messy, isn't it? They're not really dots. There are holes there, but there are not clean dots. Let's try 50%. Well, still a bit messy. We need to go back and just remind ourselves. So that's what the CO2 laser was doing. I mean, they're not exactly 0.1 dots, but they're getting close. They're about 0.12 because they've definitely got a gap between them. But also they haven't got a hollow centre. So maybe we could back off on the power even more. Or possibly lift the focus right up by maybe 10 or 12 millimeters so that we're only using the tip of the high energy part of the beam. So we've still got another couple of things we could try. You can already see at those settings there is no comparison. Fibre laser is relatively rubbish in relation to the CO2 laser. The previous one was done at 100% power and 2000 millimeters a second, because I don't think the speed has any effect on it at all. The pulses are still there at the same power regardless of the speed. This is not like metal where you're trying to build up the heat. You just want the power per pulse. And as we switch the beam on, the power is there instantly. We're going to run this now at 30% power and see what effect that has. We'll give it one last shot at 60% power and we'll go back to 400 millimeters a second. Just so that we can say we've given it a fair comparative shot. There is no point in coming onto this machine and doing it at 400 millimeters a second because I can do it on my other machine at 400 millimeters a second, so there's no advantage to going down this route. Well, yes, it's better. And if you didn't have anything to compare it with, I suppose you'd think that was quite good. But when you see what the CO2 laser can do, this is still rubbish. As we mentioned earlier, just look at the definition of the hairs, all the fur on the CO2 one. What have we got on this one? Nothing, just a bit of a blur. Now, just in case you think I'm giving up too easily, I've also tried playing with the focus. So those people that think they're putting the thing out of focus when they lift it up by 2 or 3 millimeters are sorely mistaken, because look, I've raised the head up. In other words, I've put the focus down below the focal point. but this is not a reflective material, so let's not get too concerned. And I've actually dropped the focus 22 millimeters below the focal point by the time I get to here. And yeah, it's a very slightly blurred, but we've still got sufficient power in the center of the beam to actually put a reasonable mark on this slate. Food for thought. Focus is not what you think it is. Stop. It's another day. I'm older, I'm greyer, I'm fatter, and I've had a thought. I was just about to say that this machine can't do this sort of work. And then it just doesn't make sense. It's got all the capability to do the job, but somehow or other, it's not giving. I think in reality, it's me not understanding. I suspect we have a little bit of a problem here. Number one, I understand what I'm trying to achieve. You might not. So therefore, what I'm going to do, I'm going to take a break here, and we're going to go back to the beginning and try and explain to you the basic theory behind photo engraving on these laser machines. Because in essence, it's quite simple when you understand it, but it's a bit like riding a bike. If you lift your feet off the ground, you'll fall over. You need to do a bit more than lifting your feet off the ground. Many years before photography became available, newspapers could only print text, black ink on white paper. This became a problem when they wanted to put pictures into their newspapers. The only way that they could generate pictures was like this. They had to get copper plate scribed and filled with ink so they could get their black ink onto white paper. Now that's an artist's job, a very skilled job to do that. So it was quite a few years before they managed to solve this problem and create ways of breaking up that picture from a continuous analog scale, which went from very dark brown, nearly black, to almost white. It's a sepia. It hasn't got a complete black and white colour range, but it's got a very wide colour range. There are just gradual changes of tone across the whole of the picture. So somehow they had to break that image down into black and white. Now there are many early attempts, but eventually they came up with a process called half-tone printing. Half-tone printing allows you to break that picture down into a selection of dots. This whole principle of half-tone printing relies on your brain being fooled and filling in the gaps between the spaces. It does basically a colour mixing of black and white into various shades of grey within your brain. So depending on the size of the dots that you've got in the black gradually changes to a sort of grey, and then the grey, the mid-greys here, change to white as the black gets less and less. That is a very crude representation of what the half-tone printing principle is. The problem with that, when we try and apply it to our laser system, we've got small black dots and we've got big black dots. Now the only thing that we can do with the laser machine is make dark spots, or we can burn something into the surface of a material. We can only create one colour generally. Now a couple of the large industrial type laser machines base their photo engraving software on this principle, but it has a major weakness. You can't produce different sized dots on a laser machine. Sounds pretty obvious, doesn't it? But before we get on to the details of that, this picture here, although it's an analog picture, has been reproduced in modern times to go onto a computer. So therefore, it is no longer an analog picture. And if we zoom in on this, you can clearly see that it's not completely analog, it's digital. It's made up of little square blocks called pixels. And this is the modern way in which photographs and images are stored and used. Now, isn't that amazingly detailed? What I'm going to do is we're going to analyse this picture to try and illustrate several points. First of all, I'm in Photoshop here, and it gives me the opportunity to find out exactly how this picture is constructed. If we take a look at the top here, we'll find that the picture contains a total of 21.7 million pixels of those little squares that we just saw. Now, you can't see any squares on there, can you? If I zoom in, there we go, look, you can see the pixels there. At the moment, it says the resolution of this picture, it looks a stunning quality picture, is 300 pixels per inch. I wonder what happens if I change that resolution to 10 pixels per inch. Do you think the picture is going to get better or worse? There we go. Trust me, I've changed it. I've cancelled it, and we'll come in and we'll look at the image again. Image size, 10 pixels per inch. 21.7 million pixels. Still the same number of pixels that we started off with. The only difference is if we look here at the width of the picture, it's now millimeters, 8,790 millimeters, 8 meters wide and 5.5 meters tall. Let's just change that back to 300 where it was. Where is the 8 meters gone? It's now 293 millimeters. The very important point I want to make here is that pixels are not fixed elements. A pixel can be as big as your imagination. I can have a pixel that is a metre square. You would see that picture from 10 miles off probably. It would still have 21.7 million pixels, but the pixels would be huge. If you got up close to it, you would not be able to see what the image was. The bigger the pixels, the further away you have to be to see the image. So by that understanding, if you're only going to look at it at arm's length, you need a high resolution image. But if you're looking at it as a billboard, for example, you could find that the pixels on a billboard might be 1 millimetre square if you walked up close to it. So that's important feature number one. Pixels are as big as you want them to be. Okay, well, we'll come back to that one shortly because that's an important feature when it comes to deciding what we're going to do with our images. Here we've got a coloured image. Now, we can't work with coloured images on our laser machine because we've already decided we've only got two opportunities. We either burn or we don't burn. We're effectively doing the same as an ink image, black or white. White is nothing and black is ink on a background. So the first thing we've got to do with this image, if we want to use it for laser printing, is we've got to take away the colour and turn it into something called grayscale. Okay, discard the colour information, and now we've got a grayscale image. Now, grayscale is an interesting point because unlike sepia images, they run from black to white and there are no steps in between. It's all completely gradual. With the grayscale system, black is defined as number 0 and white is defined as 255. Well, there's 254 shades of grey between black and white. So there's a total of 256 colours in the range. Every one of these has a different colour, a different shade of grey. Each one of these little squares has got a different number attached to its colour. And every one of those pixels is mapped into something in machine memory, in your computer memory. Although we've got individual blocks, pixels there on that screen, we can't work with them because we can only produce black and no black, i.e. white. There is a different sort of halftone printing. It's something called stochastic halftone, which is basically random halftone. This is patterned halftone printing, where you've got a regular pattern and different size dots. Now, stochastic halftone printing is exactly the opposite to that, and let me just show you. I'm going to first of all take this image and I'm going to turn it away from being a grayscale image into being something called a bitmap image. Now, the resolution, I'm going to leave it at 300 at the moment, pixels per inch, and we're going to use something here called a diffusion dither. We'll just say OK. I've just destroyed the image. Well, no, I haven't, not really. What you see there is something called an aliasing pattern. It's the mixing of the pixels that are in the background of the image with the pixels that are on the screen that you're seeing. As I change the magnification, look, it goes back to normal. So if I zoom in now, we'll see what's happened. Every one of these pixels that we can see here is either black or white. We can now work with this on our laser. If we just consider one of those lines across there, look, we can scan across there, and here we are. We can turn the computer on and we can burn a black line. We can turn the computer off, nothing. On, black line. Off, nothing. On, off, on, off. And that's the way the image is sent down from here to your computer. Just a series of on-off signals that correspond with the Morse code that you see on the screen. So it's really very simple. The problem is the size of that pixel. What is it? Well, remember what I said? That pixel can be as big or as small as you want. If I made that pixel, for instance, 100 millimeters square, could I print it with a single dot? No, obviously. So, in essence, what we're saying here is the size of the dot that we can produce with the machine, it controls the resolution of our image. The resolution of our image is controlled by the size of that pixel, that single pixel there. So if the smallest dot that I can produce is 0.1 millimeters, there will be 10 of those dots in a millimeter. And there will be 254 of those dots in an inch. So therefore, what I've now got to do, I've got to come back to this image and I've got to set the image size to 254. Now, it won't change anything on this screen, but what it does, it changes the physical size of the pixels, and it will actually change if we take a look again. And if we look again, you'll see that first of all, it's changed the number of pixels. And the resolution is 254, but the size of the image now is 219 by 346. Now, if we don't want an image that size, then we'll have to change it. So now I could, if I wanted, tick these boxes to constrain the image, and let's just say I wanted an image that's 100 millimeters wide, 120 millimeters wide, 120. There we go. So I've got 120 wide, 75 millimeters tall, and it's still got 254 pixels per inch. I have not changed the resolution of the picture. Okay, and you'll notice the number of pixels has now dropped even more. And that's an image which we can print, because A, we can produce dots that are 0.1 millimeters diameter, and B, it's a size that we can get onto the machine. Okay, so what you're looking at here is a very crude representation of my little dot test pattern. Now, it's been very carefully designed, this test pattern, for several good reasons. First of all, I want to be able to visibly, quickly check the size of a dot, estimate the size of a dot. So I've made my pixels here 0.1 millimeters wide. The gap between the pixels is also 0.1 millimeters wide. So that's effectively a black pixel, a white pixel, a black pixel, white pixel, like that. So all these are black these images that I've got on here. The way your laser interprets these is very simple. It comes along here and it gets to this point just here and it switches the laser beam on. And it draws a burn line until it gets to here and then it switches off. Because when there's white, there's no laser beam. On, off, on, off. The same applies to all of these. They're all on for black and off for white. But there's a fundamental problem here. We can't, first of all, manufacture square pixels with our laser. We can only produce round burn dots. And there's another problem. When the laser comes up to this point here, it says switch the beam on, which it does instantly. But of course, we've got a round dot. It gets to this point and it says switch off. But again, we've got a round dot. Here, here, on, off, on, off. Now, it might not seem too much of a problem to you along there because they're still dashes. But hang about, that dot is half a pixel hanging off the end. And we've got 1 pixel gap here. So if I've got half a pixel there, half a pixel there, half a pixel here, and half a pixel here, like that, with my dots, then how much gap have I got between the pixels? That's a problem, because remember how the brain is working? It's looking at the overall colour of the background, which is white, and it's looking at the overall colour of the foreground, which is black, and it's mixing those two together in your brain. So the more white in the image, the lighter the grey you will see. And the more black in the image, the darker the image will be. Do you see the problem? We've lost our white between the pixels. So we're automatically, when we're doing photo engraving, where we've got lots of these pixels sitting very close together, we're automatically going to create a dark image. And that is why you will find with every single piece of photo engraving software, there is a fairly significant chunk of lightening or brightness control involved to try and enhance the image and reduce this effect. I have to admit to being slightly, very slightly involved with some of the early development work in another piece of software called Lightburn. Very clever guy designed the software, and he's done a fantastic job of replacing virtually every part of RDWorks and making it 5 times better than it ever was, with all sorts of extra features. He identified this problem and decided that the right thing to do would be to delay the start of the beam. So he shifted the start of the beam along and finished the beam half a pixel early and half a pixel late. So that now you get the start and the finish of your pixel at the right place. The problem is, when you subtract half a pixel off of there and half a pixel off of there, you've got no pixel. So you get no dot. And that was a fundamental fault with his logic. Everything that was a single pixel disappeared. And it changed the quality of the image completely the opposite way to what was intended. You will always have this issue and you will always have to lighten your picture. Now this 0.1 dimension for this pattern has been very carefully chosen based on what we could possibly achieve on a CO2 laser with the lens system there. You can get less than a 0.1 dot under certain circumstances with certain materials, but in general the smallest dot you'll be able to burn will be 0.1. And therefore the best resolution that you can create your image at is 254 ppi, which is a 0.1 resolution. Pixels per inch equals 25.4 millimeters. So if we've got 0.1, it means we've got 10 of these pixels per millimetre. So if we multiply 10 by 225.4, we get 254. So that's how we arrive at these numbers. Now, good quality photographs are typically 300 pixels per inch. The essence of what we have to do to copy that photograph is to make sure that we have dots that are 0.1, so we can get 254 dots per inch, so that we can immediately copy every pixel with a dot. That's a very key part of photo engraving. You can't make the dots bigger than the pixels, because if you do, they will overlap like this, and they will occlude the background, which is the thing that's giving you the impression of light and dark. You change the density and the colour of your image. I did say that it was very simple, and I did say that it was very complex. This is the complex part. This is the simple part. Very simple. One dot equals one pixel. So look at the other way round. Decide the size of your dot, and that will tell you the resolution of the image that you can reproduce. Pixels do not overlap on the screen, therefore you cannot have dots overlapping on your material. Now, I did say that I would come back to this image here, which, as you can see it quite small, you can see that it runs from black, grey through to white. And we did say that some of the big companies use this idea for their photo engraving. It's quite economical on code, but it's not particularly pretty as an end result. It gives reasonable results, but not quality results, in my personal opinion. There are people that claim they can print 1000 dpi. Now, 1000 dpi means we're going to have a pixel or a dot size of 0.025. That's about the thickness of a human hair. That's pretty incredible. Nobody in the normal world can produce dots that small with an industrial laser machine, or even one of these hobby laser machines. The best you're going to be able to do is probably 0.05, which is probably close on 500 dots per inch. But let's just assume that they think they can do 1000 dpi. Well, if this is one dot, you won't see it. 3 or 4 dots, then you might see it, because what happens is it's going to take a huge amount of time at 1000 dpi, because what happens is you've got 1000 dots across this way, and therefore you must have 1000 dots down that way, because this is a square pixel. And 1000 lines this way is going to take absolutely ages to scan backwards and forwards. These blobs will be built up from these very, very small dots that they supposedly can put down. So it's going to take a huge amount of time to scan across this image. Well, very, very quickly, we'll just zip back to this lovely image here, which is the grayscale image. Now, it is possible to try and work with a grayscale image, depending on the material that you're working with. For example, an organic material such as wood or leather has got a scorching range from very light scorching to burnt, dark brown. So there is a colour range that you could exploit to try and match the 256 shades of grey that are in this image. And what that means is, instead of putting dots down, dot, 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 all of the same intensity, what you would try to do is every time you moved across a dot, you change the power in the pulse. So it is possible to do grayscale engraving as well, but it's nowhere near as clean, neat and efficient, from everything that I've tried and tested, as proper dithered binary engraving. But I thought I'd just mention that, hey, that's not the be all and end all what we're trying to achieve. But of course, on things like Slate, where we've only got one colour, grey and a background which is dark grey. If you're using acrylic, you produce white on a clear background. So what I'm saying is there are many materials around which are what I call binary materials. They've only got two natural colours anyway. It's only the organic materials where you've got a possible colour range that you can exploit to produce grayscale engraving. Right, back at the machine, let's try and make some sense of what we have observed earlier under the microscope. Now, I was trying to run at 2000 millimetres a second because, as I said to you, this machine is incredibly fast at the way in which it builds up its pulses. Unlike the CO2, the pulses will happen instantly. To travel 1 millimetre takes roughly half a millisecond. Now that's just a starting point to make mathematical life nice and simple a little bit later on. We've got a 2 nanosecond pulse. Now that means we're going to get a pulse every roughly microsecond. I know it's 850 rather than 1 million pulses a second, but hey, let's not argue too much about that amongst friends. For rough maths, it's good enough to say 1 million pulses a second. Now our pixel is only 0.1 millimetres wide. It might only be 0.1 millimetres wide, but as far as this machine is concerned, it's a long line. It's a line that is 0.1 millimetres long. So how long does it take to travel 0.1 millimetres? The answer is 0.5 milliseconds divided by 10, because there's 10 of these in a millimetre. So that means it takes 50 microseconds to travel 1 pixel. But we're producing a million pulses a second. So therefore it's burning 50 times across that 0.1 millimetre pixel. But we've already determined from our observations under the microscope that when we fire the laser at this slate, it produces a little volcano which produces when I say a burn spot, I mean a damage zone of 0.1 millimetres. That's a rather familiar number, 0.1 millimetres. That's the size of a pixel. But hang about, we've just talked about that. 0.1 pixel with a 0.1 dot means it's going to stop and hang over the end of each pixel by half a dot. And isn't that what we observed? We observed all the dots joining up. So we're never going to win with this approach because we're always going to have this half a pixel overlap. It doesn't happen on the CO2 machine for various reasons. The most obvious is the fact that we don't get this first half dot overlap because there's always a delay in the pulse build-up. Something that I've noticed a long time ago and never had any occasion to use it, want, or if you like, be curious about it, is something here called drill mode. Now that sounds interesting, doesn't it? Drill mode. I'm wondering if I've got any control between drill mode. We've got 0.1 milliseconds set by default. Milliseconds, that sounds like years in terms of the response speed for this machine. So yeah, I thought, well, maybe 2000 millimetres a second. How long a pulse do I actually need? And I played with the numbers and I finished up with something like 0.0005 or something like that. Some stupid number of milliseconds. Did it work? No. Absolutely nothing. Back to the drawing board. That was a dead end. Not wishing to give up on this, I felt that somewhere on this machine there must be some way of doing what I need to do. Drill mode seemed to offer the most likely possibility. So I went to the manual and tried to understand how drill mode worked. Now, the good news is It's something to do with scan mode, which is great. So it's not a mode on its own. You can actually use it with scanning. And here it is, 0.1 default milliseconds. Select this mode to define in microseconds. Hang on, that said milliseconds. Now it begins to make a bit more sense. I was putting such a short pulse in that I was getting nothing out. So if it's actually microseconds, I was putting in like nanoseconds of pulses, which are not going to do me any good at all, because they're not repetitive, they're just once. Well, how once are they? Select this mode to define in microseconds how long the laser is kept on for each point of the image that is marked. I wonder what that means. That sounds very Chinglish to me. And then we come on to the obvious. Some materials require longer and shorter exposure times to achieve good marking. Well, yeah. Increasing the drill mode time will sometimes create a deeper but lower resolution mark. Hang on. Lower resolution. Prolonged drill mode times will significantly increase the overall time required to complete the mark. So that seems to imply that there's no relationship between speed and drill mode. I can specify 2000 millimeters a second, but I'm not going to run at 2000 millimeters a second. I'm going to run at, and here's where I think the trick comes in. Look, fixed DPI. Well, I've already got the DPI fixed for my images. I've fixed in X 254 because that's the image. I'm fixed in Y 254 because that's what my image is. So I think with the merest bit of luck, when I now interpret this, this is what I think I'm going to get. I think by specifying 254 ppi, which is a fixed interval in X, and 254 ppi fixed increment in Y, I'm actually defining my pixels to sit on a grid like this. And if my pixel sits on the intersect of one of these grids and is black, remember what black does? Black turns the beam on. So if I specify a duration time for drilling, I'm going to get at that intersect a drill hole, and then I'm going to get another drill hole there and there and there, and that means when I get a single pixel, I'm not going to get a lump out the end, I'm going to get a drill hole at the intersect point. Wow, now this is looking very, very... I'm getting quite excited now. Is it too good to be true? Let's give it a try. I presume that the pulse and frequency numbers are still relevant to the drilling pulse itself. So if I specify a 2 nanosecond pulse, I'm going to get a pulse every microsecond. Just one 2 nanosecond pulse. So if I specify 1 microsecond, I'm only going to get one 2 nanosecond pulse. And hopefully it's going to be one 2 nanosecond pulse right in the middle of a pixel. Well, as I've said to you before, this is not a tutorial. This is you looking over my shoulder and either falling flat on my face or succeeding. So let's push the button and see what we get. Ooh. I'm going to do something silly for a minute, because I think
I've got to go the wrong way. I think I want to go shorter time period, but I'm going to go a longer time period just to prove a point to start with. Wow, yes, you see it took a lot longer. So it's not speed related, it's duration of pulse related. You will absolutely love this when you see it under the microscope. Now we're going to go the other way. 10, 1, 0.5. Straight to 0.1. Let's do that. Let's go too far. 5 right down to 0.1 microsecond. Now that was quick. And to be honest, what I can see here is really exciting. Well, certainly quick again. And look at those under the microscope now, because they are far too interesting for me to keep to myself. Here's what 10 microseconds of drilling looks like. Now do you believe that this process produces glass? Is there any more proof that I need? Look at it. In fact, I accidentally touched that with the microscope, and look, I've cracked the glass. Okay, now let's take a look at the next one, which was 1 microsecond. Okay, now look, we can see the set of holes along the dashes there. They're literally just piercing holes. They're not running along continuously. Wow, you see, at 1 microsecond, we're starting to see the dots, but they're still squirting out enough glass so that they overlap. We're going to go down to 0.5 microseconds. And the dots are a lot cleaner. Now we're getting a bit of separation between them, look. We're still squirting out too much from the little volcanoes, so we're still putting too much energy in. Let's go and look at the 0.1 microsecond. Everything is getting a lot neater, isn't it? And look, we can see every one of those pulses along the dashes here. I mean, it clearly indicates that we have got drilling taking place at the coordinate intersects, as my drawing indicated. Wow, look at those. They're lovely dots, aren't they? Well, now I say they're lovely dots. There is a problem with them, actually. They're nice size, and they've got a nice white edge to all those dots. They're lovely and separated. They will produce a great image. I'm absolutely sure about that. In fact, I'm sure it's going to actually beat the quality of the image that I get from the CO2 laser. But, and there is a but, look at this. Can you see that there? A black hole. It's a donut. But it's not a white donut, it's a black donut. Now remember the way in which the whole of this principle of photo engraving works. It's the relationship between white and black. So here we've got a background, and here we've got, if you like, a white foreground. But we've also got some black background showing to you. No, I know it's not the background, but it doesn't matter what it is, it's black. So it's adding to the blackness of the image. So it's actually going to downplay the quality of the result that we get. It's going to be a slightly dimmer result. Now, I didn't realise that when I was looking at them under the magnifying glass, but we also did a couple of other trials, and I might have to go and do some more. What did I do? I changed the power, didn't I, to a different power setting. Yeah, no, that's not going to work, is it? Because look, I've got even bigger black holes in there. Now, I know this is a very minor detail that probably most people wouldn't even bother to think about, but it is an important part of viewing these images. It's something that I've become very, very aware of. And those holes are just unacceptable. There's all black and no white. By increasing the pulse length, I'm just making the hole bigger and the squirt, the white glassy effect, less. So let's just move on to the next one, which was a 2 nanosecond pulse, but at 80% power. Now, will that reduce the central black part? Well, it certainly looks as though it's having an effect, but has it made them so? And looking at those, you know, I think they are less than 0.1. In fact, I can see they're less than 0.1. They're probably somewhere in the region of about 0.08. 1 inch is 25.4 millimeters. 25.4 divided by 0.08. 0.08 equals 317.5. I might set the resolution to 300 and see what we get. Well, I'm extremely pleased with that result, and yeah, okay, egg on me face. I thought it was going to fail. It hasn't. It's come up trumps. So let's go and do the real test, which to see what the image comes out like in comparison to the CO2.
Well, that's probably about half the time that it takes to do on the CO2 laser. Even though I've got my CO2 laser well pimped up, and I thought it was doing very well, this is doing a superb job. It's really quite interesting that when you look at the actual dormouse itself, it seems to be slightly darker than this one. Which one do I like? It's very difficult to choose between them, to be honest. This one's slightly whiter, dots in the centre of the little spots. That's what I think is making this one darker. But it's still a lovely image. Well, I think we'll finish on that happy note, should we? I think we've found the secret of engraving slate on the fibre laser. Drill mode. Thanks for your time and patience, and I'll see you on another adventure next time. Bye for now.